Welcome back. Example 5. Find the volume of the solid obtained by rotating the rotating the region between the curves y equals x cubed and y equals square root x about the x-axis. So y equals x cubed is this curve. Y equals square root x is this curve. You want to take the region between these two curves, that is this region, and rotate it about the x-axis. For this, first we need to find this intersection point. Okay, this intersection point is 0, 0, as you can see. What about this intersection point? So y equals x cubed and y equals square root x. You obtain the intersection point by setting x cubed equals square root x. Square both sides, you get x equals x to the power 6. Get x to the power 6 minus x equals 0. Factor. X is a common factor. X to the 5 minus 1 is 0. You can factor this. X to the power 5 minus 1 is x minus 1 times this entire expression. X to the 4th plus x to the 3rd plus x squared plus x plus 1. Now notice, this factor x gets me x equals 0 as a root. This factor gets me x equals 1 as a root, and these are the only two real roots. This last factor, all the roots are complex, non-real, all right? So, when x is 0, y coordinate is 0. You can use either of these expressions. Notice, y, they intersect here means you could use either one of these expressions. So when x is 0, y is 0. All right. When x is 1, y is 1. Either one of these expressions. So you get the point 0, 0 and the point 1, 1. So that's your intersection point, and this is 0, 0, another intersection point. So this region, you want to rotate it about the x-axis. When you do that, you get a solid which looks like this. So that region has been rotated about the x-axis. So you get a solid like that. You see, filled in these regions, but a hole in the middle. So it's like a cup with a hole in the middle. So at this point, notice I have rotated about the x-axis. So the cross sections are vertical. So whichever axis you rotate about, you cut perpendicular to that axis, you see. So the cross section is, each cross section is a circle within a circle. The inner circle because of that cutout piece, outer circle because of the outer edge. So the solid of rotation is supported on the x-axis from x equals 0 until x equals 1. That's the other intersection point. So 0 to 1. Each thin cylinder, so when you take vertical slices, you have width of delta x because that's the change in x value, horizontal delta x. And for each x from here to here, the cross-sectional area is the difference of areas of two circles. There is a circle outside and a circle inside. In other words, the region is the region between two concentric circles. Now, what about the outer circle? Outer circle is center here to here. So that's square root x. What is the inner circle? From here until here, which is x cubed. So the outer circle has radius square root x. Inner circle has radius x cubed. Okay, I hope it's clear. You're looking at y coordinate, which is square root x. Vertical distance is y coordinate. It's square root x for the outer circle And for the inner circle, you use this underlying curve that is x cubed. So the area of each cross section is pi outer radius square minus pi inner radius square. So that gives me an x, and this gives me x to the power 6 with a common factor of pi. The volume of each thin cylinder is my area times its width. In other words, volume of the entire solid is integral 0 to 1. I hope you remember why the limits are 0 to 1. It's because x coordinate goes from 0 until 1. Okay. Total area, cross-sectional area dx. Now all that remains is simplification or calculation. So pi is a common factor outside. Antiderivative of x is x squared over 2. Antiderivative of x to the power 6 is x to the power 7 over 7. Plugging in the limits 1 and 0, 0 fetches me nothing. Simply substituting 1, I get 1 over 2 minus 1 over 7, pi times that difference, which is same as 5 pi over 14 cube units. Okay, so that was example 5. So notice, first step is to find intersection points. When you rotate about the x-axis, you're going to get cross sections which are vertical, and you're going to take integration over the x-axis. So 0 to 1 delta dx and cross-sectional area. All right. Next example will come in our next video.